Hello, welcome to another problem session. Today we're going to talk about how do you find the variation of intensity. So here is a screen and we're just looking at the XY plane. Of course, the whole thing is three-dimensional, and we are going to do diffraction of light. You can think of a light. You can think of any other wave. We're just going to take light. And what happens is light waves are coming here in the back of this, and there is a slit through which the light waves actually have to pass. And there is a screen here. This is screen, and so screen is also three-dimensional. Screen is also three-dimensional. A large screen here, you might say large screen here, and is three-dimensional. And on here, if you take a cross section, this is XY plane, XY plane cross section. In that cross section, you will see that there is a light intensity, and then actually intensity changes and kind of it keeps varying periodically. Periodically the intensity disappears. For instance, here it disappears, here it disappears, here it disappears, here it disappears, here it disappears. So the places that disappear, they are the minima of the intensity. I mean, ideally it should be zero, but in practice it's like a minimum value intensity. So you have a maximum intensity, so max, and you have a min, and then next max, and the next min, next to next max, etc. And these are this is called diffraction pattern. The whole thing is called diffraction pattern. And you can see the variation of intensity. Eventually it becomes so dim you can't you won't be able to tell. And because the slit is oriented this way, this intensity is kind of, if you look at it, it would be, so over here you'll have exact copy of this over here like this, and over here it's going to be like this. Over here it will be like this, and so on and so forth. So you have a maximum, it's kind of like a hill on here. Okay, the formula for any angle theta and given lambda, so let's write down k is 2 pi over lambda, right? So I can write down lambda or k. I'm going to define a quantity beta, which will be k times the width is b. So this slit width I'm going to take is b. Okay, so kb sine theta over 2. So I'm going to define this quantity because it turns out to be this is the quantity that comes up. Instead of theta, you have beta. So over here at point P, I wanted this, so I can compute from the theta to point P what the corresponding beta will be. So we find the intensity on the screen is a function of theta through beta. So it's like and so whatever the intensity is at this angle, you can see that theta equal to 0 corresponds to beta equal to 0. So whatever the intensity is in the symmetric point, the maximum intensity, and then you have a sine of beta over beta square. So that's the intensity. And this beta is a function of theta this way. So if theta varies, so when theta varies, beta also varies, right? So if you look at theta, I mean, theta can be, maximum it can be on this side is plus pi over 2, and on this side minus pi over 2. So the theta is basically in here is minus pi over 2 theta less than pi over 2 or pi over 2. So so at one place where sine will be 0, so if you look at the sine of theta in that, you know, so you have theta, so it's going to go from minus 1 to plus 1 pi over 2 minus pi over 2. So this is one place when theta is 0, sine theta will be 0 and beta will be 0. So you'll get sine 0 over 0, and you think that would be a problem, but actually this function, you have a sine x over x, and you have a limit x goes to 0. This function is actually 1. There's a name of this function. It's something called sinc function. Okay. So all the other places, this beta is not 0. Okay. However, whenever sine of beta, if beta is 2 pi, say beta is pi, okay, then sine of beta will be 0, and sine beta over beta is now well defined. This is pi now. This is going to be 0 over pi, and this is okay to be 0. So that's the direction that we will see a minimum, right? So this formula tells us where the minimum will be very, very simply whenever beta of theta, whenever beta of theta is pi, 2 pi, 3 pi, all this times sine of beta will be 0, but beta is not 0. That means sine beta over beta will be 0. That means intensity in that direction will be 0. So if you can do plus or minus here, plus or minus here, plus or minus, and it's the same answer you're going to get. So these are the minima here. Very easy to see from this formula where the minimum will be. And okay, so let's see what the let's look at one of this. And so we have a kb over 2 sine theta equals to, say, pi. So this is one minimum number 1. Okay, so we're looking at that particular minimum, that direction. Okay, what is the theta correspond to that? So k will be 2 pi over lambda. So the 2 cancels 2, pi cancels pi. So it says b times sine theta equals to lambda. In a previous video, we used the symbol d for the width of, right now I'm using b. So this is the answer where the minimum will be, minimum number 1. You pick any of the minimum, you can see for minimum number 2. So is kb sine theta over 2 is 2 pi. Okay, so this is again same deal, 2 pi over lambda, and these 2's go away. So, and this pi goes away, and so this is b sine theta equals 2 lambda, and this is minimum number 2. So the minimum very easy to get from this formula. I will show you towards the end of the video how to derive this formula, but right now just exploring minimum and maximum. How about the maximum to get this formula? Let me erase it and show you. Okay, so where would these first one is very easy to get. You can see the maximum here is going to be theta equal to 0. So maxima. So this is diffraction maximus. One is very easy to get because this will be 1. So beta equal to 0 is one of them. That corresponds to theta equal to 0. So that's one maxima. How about the other maxima? Not so easy to see it, okay? So we will say di d beta equal to 0. It will have catch all maxima and minima. But minima, already we found that beta has to be n pi, n equals to plus minus 1, plus minus 2, plus minus 3, etc. So minima, we already found that. So when we find the answer from here for all the maxima minima, and we can kill this out, we'll all get the maxima, right? So one of them is like that, and the rest I'll get. So when I do this, I get 2, let's call this I0 sine beta over beta, and then this becomes a cosine beta over beta minus sine beta over beta square equal to 0. Now this is not 0, so just so when I vary beta over beta, so either this is 0 or this is 0. So there are two choices here. So sine beta over beta equal to 0, that's let's call it choice number A. Choice number B is this thing, cosine beta over beta minus sine beta over beta square equal to 0. So this one definitely says beta is not 0, because 0 then this can be 1, and so beta is just n pi from here, and n equals to plus or minus 1, plus or minus 2, etc. So this is of the minima. So we don't want this already found out, so this is a choice. And we all say multiply by beta square, everybody. So beta is in the denominator, so we are not looking at beta not equal to 0. So we just multiply this. I have beta cosine beta minus equals to sine beta, and so we need to solve this problem. How do I solve this problem? How do I solve this? This says tangent beta beta equals to tangent beta. So this is a pretty hard problem to solve, and one way to solve this is what is called graphical method, and let me illustrate that. Okay, we want to find out the values of beta for which this is true. This is true, right? So that will correspond to, in addition to these, those will be the maxima. So one way to do it is plot the left side and the right side against beta. So, and So let's see. This is say pi over 2. That's where tangent of beta will blow up. Minus pi over 2. Tangent of beta will blow up. Then another, this is pi. 3 pi over 2. Tangent of beta will blow up again. Minus pi. Minus 3 pi over 2. So the left hand side beta is just beta is just going to be diagonal thing, goes through the origin. This is going to be beta. How about tangent beta? Tangent beta will be it's going to be negative infinity and it's going to be like that. So this is only one place they match. So the beta equal to 0. That we already know. That's not a new solution. Over here, you can see that it's going to go to infinity, and this going to go minus infinity, and over here is going to match, and then it's going to go at the 0 is going to cross it, at the pi is going to cross to 0, and that's where it's going to match. So it's going to match very close to minus 3 pi over 2, very close, and it's going to match very close to 3 pi over 2. So that's another answer. So the beta, that this answer is 0, and then very close to 3 pi over 2, and very close to minus 3 pi over 2. And you can see it's going to be like that. I'm sorry, this like that. So that's going to be 5 pi over 2. So very close to 5 pi over 2, and very close to minus 5 pi over 2. So this is called graphical method of solution. And let me see that. So these are all will be so-called maxima. So this particular formula that I wrote down here actually tells us where the maximum minimum. It also tells us what will happen in between, because if I give it some number 1, say just scale it to 1, and this will vary with theta. So it actually, if I were to or want to know how things are varying with theta, this will tell us, right? So for instance, if I plot this theta and plot this I, of course you can say for each theta what's the beta. So when the beta is pi, when beta is pi, for that corresponding theta I'm going to get 0, and when beta is minus pi I'm going to get 0 for that theta. But theta is there's a relationship like that. In the beta we know how this will behave very nicely, and say this is maximum. So this is the first, is going to go to like that, and then there will be a maximum here, and then when I go to 2 pi in this guy, for that theta is going to 0 again. So it's going to be like this, and then like that, and same kind of thing on the other side. When beta is minus 2 pi is going to go to 0. So and so on and so forth. Now it actually, when you plot this out, if this is 1, this peak is very small. It's like 0.054. So like it's unless it's very intense, you won't be able to see these things. That's why you need intense light to see this. And this one is even more it's much smaller peak, and pretty soon kind of dies down very quickly. Okay. All right. So now I want to show you how I get this formula. Okay. All right. Okay. This is a derivation, so it's going to be a lot of mathy things now, and brace yourself. It's going to take some time to do it. All right. So I hope you don't get discouraged by it. So let's look at it. What I'm going to do is this is where the wavefront is inside the slit. So that's the slit. And I'm going to look at a small piece of it and treat this as a point, okay, point source. So this is going to be at y and y plus dy. So this is a thickness is dy. So the intensity amplitude will be here. We can think of this amplitude here is a0 dy, or amplitude here, and then it's gonna be a spherical wave, and over here when it reaches, let's call it electrical wave at point P. Use little d to say it's going to be corresponding to infinitesimal wavefront. So at P is, I'm going to see at P. Let's see if this distance is, say, call it R. And I'm going to call this distance from the center to that point a capital R. And of course, this is L and this is theta. Okay, so this will be a spherical wave with amplitude. This is going to drop, right? So a0 dy, and it's going to drop by r, and I'm going to say that over there phase constant for everything is 0. Okay, so this wave phase constant was 0 at this. That's the configuration for simplicity. It doesn't make a difference actually, but the phase constant is there as long as all of them are correlated. Okay, so cosine theta, I'm going to get k times r. K is lambda times k is 2 pi, so k is related like that, minus omega t. So I'm going to look at one frequency, omega times time period is or omega over frequency is 2 pi. Okay, so there's a relationship. So okay, now I want to see what this can make this into intensity. This is the electric field amplitude from this point, but I want to know contribution from all of them. So this will come out there, this will come out there, and this will come out there. All of this will come out, right? And then they will, over there, electric field has a superposition principle. Means net electric field at point P will be all the EP. This is like a formal integral, so I integrate over this to get it, but this actually means I integrate over y is along the different places. So, and you can see that where is y in here? If I integrate y, just comes out, right? So if you look at this r, point P is fixed, so depending on y, this r value is different, right? So this actually is a function of y, r is a function of y. So this, and we will, so we write down minus b over 2 to b over 2 a0, that's nothing, so it's going to come outside, dy r is a function of y, and cosine k r is a function of y minus omega t. Now this is let's see what the r is a function of y looks like. So notice I'm going to call this point a. This point I'm going to call it a. So look at in triangle OAP. Triangle OAP looks like this. So this outside is theta, so this angle is pi over 2 minus theta, and this side is y, and this is r, and this is capital R, right? Okay, so law of cosine says r square is r square plus y square minus 2y times r cosine pi over 2 minus theta. So that's just sine theta. So this is r square plus y square minus 2yr sine theta. And you can see this y is much less than r. This slit is very narrow compared to the distance to the screen. So if I pull this r square out, I'm going to get 1 minus 2y over r sine theta plus y square over r square. And now we get r, so r will be just this times square root of this. And this we can expand up to 1 power in y over r. So this is 2 powers, so I can just kill that compared to this. And so this just r 1 minus 2y over r sine theta times half. So 2 goes away, and then you have a plus order y over r, y square over r square, which I've already removed, so I don't want to carry that. So this is r minus y sine theta. Now r is much greater than y. That means this should be very close to r, and we can replace this outside here without any problem. But over here you can see that if I kr versus kr minus ky sine theta. Now kr is going to be some number, but you can see this whole argument here is modulo 2 pi. So this can be, this can be whatever big, say this is like a 1000 pi. Say this is 1000 pi. All we want is this will wash away, I mean the modulo 2 pi, so this will wash away, but this guy will contribute, right? Because I'm looking for modulo pi. So this even it's like a 0.1 pi, this is the one that's gonna become important because it's inside the cosine and because it's modulo 2 pi. So I can't really just replace this with that. We need to keep this whole thing inside here. All right. So that's actually a tricky point. Because of the modulo 2 pi, I must keep this whole thing, but here there's no modulo 2 pi, the whole thing, and in that case I just compare r with y and then this replace with r. And so let me erase this to get a good. All right, so suppose we get this. So the thing I have to do is EP is equal to A0, and this is R comes out, dy minus b over 2 to b over 2, and cosine kr minus omega t, I'm going to just keep it together, minus k sine theta times y. Okay, so doing this integral is not that difficult. Okay, but suppose we have done this integral, how do I get the intensity? So intensity at p is going to be epsilon naught, the speed of light, so this is the speed of light, times time average of ep square, time average this. So that's going to come from the electromagnetic wave analysis. So, and this is what the formula will look like, some constant, let's call it some alpha, and it's going to become sine beta over beta square. And we can recognize this alpha as value of IP when P is straight, theta equal to 0. So this alpha will just be IP when theta equal to 0 or beta equal to 0. Okay, so that's what this will go. So now to do this integral, you can just say, oh, how about this is u and maybe v, and then change to u minus py and go in there. So upshot is we work this out. I worked this out here, and I'm just gonna write the answer that I got. So I got 2 times a0 b over rbk sine theta. So when you change the variable, you get this thing down here, sine bk over 2 sine theta, and then cosine kr minus omega t. So when you work this out, you get this. Now when you put in here, so ep square time average, these guys here do not have time, so call that beta, then this whole thing becomes beta. So you can see that some constant sine beta over beta square, and there's no time here, and so this is going to be times time average of cosine square kr minus omega t, time average. So how do you do time average of this thing? Well, this is a periodic function, so you integrate over dt 1 over time period and 0 to time period. So what is the time period? Time period is 2 pi over omega. So you do this, and I guarantee you that you should do this out, and you will get an answer half from here. So this is whatever constant is, just times half. We're just going to call this guy, I'm just going to do alpha. I'm going to get sine beta over beta square. And so now we get this, and so I at p is I at theta equal to 0 sine beta over beta square. So some of these steps you have to work it out, and I didn't do it. It's a good practice for you. I hope it was clear how to proceed. This is a little bit advanced for a lot of courses, but it's not too advanced. These integrals are not that difficult to do. Just most important step, if I were to say something about where you place your learning, is the step that I have an infinitesimal dy, and this becomes a source of wave, and that wave travels over there and causes this. So this is one important point. Second important point is when r changes over here, we can replace with r. But r with approximate r, we can't replace with that. We have to keep this whole thing, and that has to do with this modulo 2 pi here. And this cosine function as a whole, the argument of cosine, you have to keep the y dependence in there. Okay. And now these are two. This is a physics thing, and this is the math. This is the math approximation we're doing. This is very important. A third step is the time averaging. That intensity is actually related to the time average of the square of the electric field for the electromagnetic waves or magnetic field. This one, both electric field, magnetic field waves are added up, and everything can be written in terms of electric field waves. And so when you do time average, is important. So then that's point number 3. This is point number 2. And fourth point is when you do this time average, how do I get half? That you have to kind of convince yourself. You can take this and do this out yourself. And one way to do this out for yourself will be to expand that, to double angle formula. Okay, so this is point number 4. So those are the 4 critical steps here, and hopefully you can complete that derivation. Take care. I'll see you in another video. Bye.